Now today we study chapter 3 about draft routines and subroutines. Firstly, to understand system calls. So what are they? You know, when you write program, maybe you want to input or output. For example, you want to input a character from keyboard, or you want to output a string of characters to screen. At that time, you can use subroutines or system calls. Of course, we don't know how to write them themselves, but we can use them for our program. With the system call, the user program can invoke system call to do the operation we want. And the operating system code performs the operations or the action we want for our program. For example, you want to input a character from keyboard. At that time, you can call track vector corresponding to importing a character from our keyboard. At the end, you have to return control to user program. In the LC3, there is the rule the trap mechanism. So now we should understand this mechanism. With the LC3 trap mechanism, you can understand the set of service routines. So what are they? As you know, with our operating system, you have many routines start at arbitrary addresses. In fact, you have 256 routines we can use for using in our program. We have a table of static addresses. This table is stored at addresses in memory from addresses 0, 0, 0, 0, 0, FF. So this table is called system control block. With trap instruction, you know, when you write the program, maybe you want to use the system call. At that time, you can use trap instruction with the trap vector. So we have a big trap vector names one of the 256 service routines. And at the end, we have a link back to the user program. That means after doing the action or the operation from subroutine, we have to return back to the user program. This is trap instructions for 1 bit. And over here we have to provide with 8 bits for each trap vectors. You know, 8 bits over here, this is the index in the table of subroutine addresses. With the 8-bit trap vector, we can get the address, or we have the index in the table. For example, when we have 12.31 hex, at that time we have the index 0031. We can go to the memory location at the address 0021 in the table. We can find out its content. This content is the address of the subroutine in the memory. And then we can go to the memory location and we can read out and to run the subroutine. But you know, how can we get that? If you want to go to the subroutine, so firstly you have to look up the start address from the table and place the address in PC. That means we have to go to the location storing the address of the subroutine and store it in PC to run the subroutine we want. But how can we get back? Of course, first we have to set address of next instruction. That means the current PC in 7, and then at the end we have to return back to the current program. That means user program, our current program. Over here we have the symbol data path for trap instructions with the LC3. Firstly, over here now you have the trap over here, and you have the trap value from B0 to B7. Okay, but firstly, we have to store the current PC to R7, and then over here, because you can get the 8-bit of trap errors, and we use a 0 extension operation, and we get 16 bits. Okay, this is the address of our location storing the address of our subroutine, and we read arm the address of the subroutine, so we store it back to PC. Okay, so over here, PC is storing the address of the first function of the subroutine you want to run. Okay, so this is the data part of trap instruction we just studied. But you remember, we have to return to our current program. So at the end of trap, normally we use the instruction jump R7 or return to come back to the current program. In fact, at the end of the subroutine, we have it. We don't need to write this instruction. So we can get the conclusion for you. We trap and return over here. The opcode of return 1100, and of course before going to trap, you must set the register PC to R7. So when you call return, we have to store the register R7 back to the current PC. So over here, we use return, and we don't need to write 111, that means R7. We don't need to write 3 1 bits over here. When you write return, that means we must use R7. But when you jump R7, you must write jump R7 for this over here. This is our program, our current program. At the beginning, when we come here, for example, you remember when we have 4 1 bit, so what do we have? You remember? Well, that means we call a trap value. That means that you want to call a trap, okay? You want to call a subroutine. For example, you have 2 3. Do you remember 2 3 hex? What you have 2 3 hex? So we have the index 0 0 to 3 in the system control plot. So we have each data that the address 004A0, and over here 40. That's the address of a subroutine. Okay, and over here at the end of the subroutine, we have the 1100. These are the return, and over here you don't need to write it because it has already had in the subroutine over here.